Our advisor is Dr. Ibrahim Hansel, and we're here this morning to present to you our project of an unmanned aerial vehicle, or UAV as they are commonly known. Problem statement was to design a flight-worthy unmanned aerial vehicle with the ability to carry a payload of onboard computer, a GPS, camera, autopilot, and other sensors and components. We were to then test this design to ensure that all components are implemented correctly and enter the design into the 11th Annual Association for Unmanned Vehicle Systems International Student Unmanned Aerial Systems Competition. This project was to be a joint venture between our team and a team of electrical engineering students. We would design the mechanical aspects of the plane, and they would design the electronic components such as the computer and the autopilot. For this project, we came up with several design alternatives. The first of these alternatives was a glider type RC plane, which is very commonly available. The design characteristics of this plane were a mid-wing configuration. It had long, thin wings, a T-type tail for elevation, a front position propeller, and a fuselage consisting of a rounded front with a narrowing conical midsection. The pros to this design were a long flight time, high altitude flight, and high efficiency. The major cons of this design were the front position propeller, which would inhibit the view of any cameras that would need to be mounted towards the front of the aircraft, and lower maneuverability inherent with these types of RC planes. The second design alternative was based off the General Atomics MQ-9 Reaper drone, which is currently being used by the United States military, the several branches, and by other government and non-government organizations across the world. This design features a mid-wing configuration with long, thin wings, a V-type tail, a rear position propeller, and a fuselage consisting of a spherical rounded nose met with a long cylindrical shell that leads to the rear propeller. The major pros to this design were a great line of sight for the cameras, high efficiency, reduced wetted area due to the V-type tail, and long flight time. The major cons of this design were that the V-type tail, while reducing drag, also increases the control complexity. And typically, scale models such as this are less stable than other types of RC planes. The third design alternative was a flying wing or delta wing type plane. This design features long, broad wings and one set of combination elevators, ailerons, or elevons as they're commonly known, on each wing, and vertical stabilizers also at the end of each wing, and a rear-mounted engine. The pros to this design were that it actually has provisions for several cameras, including a front-facing and an oblique front-facing camera, high efficiency, a large payload capacity, and a large fuselage. The major cons to this design was that due to its design and its lack of traditional control surfaces, they're traditionally less stable. Project formulation. For this design, for the project, we chose to go with the third design alternative. This design incorporates, like I said, two front-facing cameras, which allows for a large, unobstructed range of sight. And this is a necessary provision for the competition that we were going to enter. The specific model that we chose was designed specifically for FPV, or first-person video control, which made the design particularly attractive for us. We were to assemble and modify the aircraft accordingly to make sure all the necessary electronic components could be accommodated. And as a backup, we decided that the second design alternative would also be constructed from scratch. This is the timeline of responsibilities, which includes all the technical reports that we prepared, the conceptual design, all the designing, simulating, fundraising, and purchasing that we had to go through. And as to this date, we completed all of these in a timely manner. Prototype specifications were that the housing was to be able to hold all the electronic components that were necessary for unmanned control, including the autopilot, which in this case was an autopilot, the computer and electronic components, including the Panda board, which is a low-power, low-cost single-board computer development platform, the electronic speed controller, which is necessary for electric motors, and an 8-channel receiver, which was used for controlling the servos and the throttle. Also, the fuselage needed to house the camera or cameras, including its own transmitters and receivers that would send information to the computers on the ground, and other sensors. There needed to be large enough space in the rear to mount the motor, and also landing gear was a consideration. The particular flying wing that we chose did not come with provisions for landing gear, and we made the decision to leave landing gear off so as to not add any unnecessary weight.
All right, thank you, Francisco. As you can see here, this is our design for the second prototype. We constructed this on SolidWorks in order to test aerodynamics of the intended design that we wanted to use. Here's a rendered image of it. You can also see two separate images. One is a front view, and you have an isometric view, so you can get a scale as to the size of the wings that we decided to use, compare with the body itself, and also to get a size for the elevators and the rudder. In order for us to build this on SolidWorks, we first had to come custom with the aerodynamic principles themselves. In order for the basic principles, will state that in order for an airfoil to be able to create lift in an aircraft, it must be able to overcome the weight of the aircraft itself, as well as the drag over the surface area. In order for this to happen, a larger surface area for the airfoils will be able to create lift if enough thrust is provided from the engine itself. And here is a fluid flow analysis of the airflow over the airfoils as well as the fuselage. As you can see in the airfoil itself, a low pressure system above the airfoil, which is a custom with many designs that are very aerodynamic, is occurring here, as you can see by the increased velocity over the top of the airfoil, as well as the fuselage. For the material selection for this project, we decided to go with an expanded polystyrene, mostly due to cost, as well as the weight provisions for the craft itself. Some positive aspects for the material are that it's a tough and rigid material to use. It's used in many remotely controlled RC vehicles. It's also cheaper to purchase than the expanded polypropylene that was used in the third design that we implemented. And as I said, it's very cheap and it's easy to cut and shape. Some of the negative aspects are that in shear, this plane is very brittle. It's not a very durable material to use, and it's not easily repairable, as if a crash would occur or if it would be damaged during transportation. This is the foam that we chose to buy. This is a sheet. It was sold in sheets that were 3/4 of an inch thick. They were 2 feet wide and 4 feet in length. The SolidWorks model that we had was a solid model, so we had to scale it down by each layer, in which we sketched the design onto each layer of the foam itself to then be constructed. Once all the layers were sketched out, we were able to commence the manufacturing. So for this, you can see the construction of our prototype. This is the first phase, which we had already laid out the drawings for all the layers. We began cutting, and for this foam, typically people would use a hot wire cutter, but we weren't available. We didn't have one of those available, so we used a box cutter in place of that, which worked really well due to the properties of the foam itself. After we had all of the components laid out, we then began the process of joining them together. We used an epoxy resin, and with this resin, it usually has a set time of about 15 minutes. And in order to harden fully, it takes about an hour to 2. And then you can see the before and after here, after the forming was done. This is the joined fuselage with all the components together. And the after picture shows the smoothed out surfaces that we needed for the aerodynamic principles to take effect. And this would have been our final design of the aircraft, all put together. All right. You can also see now this is our third design. This is the prototype 3 that we implemented. This is the wing type fuselage. When we received the plane from the manufacturer, it came with all the parts already inside the box. All we had to do was put it together. But one of the provisions they provided was a mount for the motor that we were meant to use. We used the motor that was already readily available in the lab, which was bigger than the specified motor to use. And in order to prevent vibration and fracture of the balsa wood, which they gave us as a mount, we decided to go ahead and machine a mount from aluminum. We used a 3mm plate of aluminum, and we placed it on top of the bracket itself so that fracture wouldn't occur during flight and something bad would happen. So during the testing, we were only able to conduct the SolidWorks analysis for the second plane, but we were able to do all the fluid simulations for that craft. Once the other plane was bought, we were able to put it together and modify it to be able to house all the components and to be able to weight balance it properly, as well as making room for all, like I said, the necessary components that the electrical team provided to us. We conducted several flights with this plane. Unfortunately, during one of the flights, our left stabilizer came loose, causing the plane to lose control, and we crashed it. This probably happened due to the excess of winds that we were flying in. There were gusts that day of around 22 miles an hour, and it was one of our first flights of the day, so it was pretty unlucky. This is a picture after of the plane. As you can see, we could not reclaim anything to be used here. Enough duct tape wouldn't have helped us. And here's Richard.
Thank you, Josh. As you can see here, our initial projected cost was going to be around $3,000. Our advisor, Professor Tansel, had told us from previous years and from information that we got from previous students that were working on this project, they had an initial budget of around $3,000 to work on this project. Unfortunately, due to budget cuts by NASA, which we were going to receive a majority of our funding from, we only had $1,500 provided to us by them. Unfortunately, due to this and also having the amount of electrical students that we had working with us as well, we were unable to travel to the competition. Competition was going to be the majority of our cost for entrance fees, travel expenses, and lodging, especially since it was pretty far distance from here. Our initial cost stayed the same, our projected cost for each one of the components. As you can see here, once we were able to finish the project, we were able, as Josh said, with the engine and several other components, salvage them from previous planes that were used. That included an engine, radio receiver, transmitter, and several miscellaneous parts. That saved us tons of money, as you can see. We were actually under the 800 and change budget that we had originally. Our major costs were actually our RC plane bodies. We had purchased 2 bodies. We also had to purchase the materials for constructing the second design that was formed in SolidWorks, as well as we saved money as well on our reports. When printing those out, we were actually able to find a way to print them and do things slightly cheaper than we had anticipated. So our final cost of $556.11 from our $1,800 budget. As I mentioned, we had received $1,500 from NASA, and we actually received $300 from the mechanical department here at FIU. Gave us a difference of $1,243.89 that were actually used by the electrical team to purchase all the internal components that they needed for their side of the project. So the testing phase of the second design was unable to be carried out due to several issues that we ran into. We received initial dimensions for internal components from the electrical team of what was needed to be carried on the plane. We designed our plane around those specifications. Unfortunately, a lot of those internal components had to be changed due to budget issues and electrical issues that they ran into, and that mean that we had to change the internals of the plane. That would have caused structural issues and would have compromised the plane during flight if we tried to fly it. But we did end up having rigorous tests, as mentioned earlier. On the third design, we were able to accomplish good weight balancing to accomplish flight with all the internals parts that we had on the plane. We had prolonged flight. Unfortunately, as was said earlier, with the unfavorable winds, we actually we lost the plane. So around the world, there's many uses for this plane. U.S. military is one of the front runners, as you can see. These planes are used for surveillance as well as many other tasks. One of the things that does have to be considered is hacking issues, that making sure that no one ever takes control of any of these planes or takes it out of the control of even a civilian situation. Also, these planes should be recovered as much as possible. That's one of the main things the U.S. military has to do, as well as any civilian issues where if they're developing components for themselves, they don't want to be losing these planes. They want to be able to make sure they either have it fly back or recover it of any crash. So these planes are actually now being implemented with neural networks and genetic algorithms. So these planes are given tasks without having to do extensive programming, and they're able to decide what is the best way to complete these tasks. What we have to make sure we continue to do is have full control over these algorithms and over these tasks, and make sure none of these planes are going rogue or deciding to do something without any control over it from a human. Currently, there's no serious threats of this happening. There's not going to be seeing any UAVs going off by themselves. So, based on what we have so far, any future work is going to be considered for the second design or the third design, whether or not to purchase a third plane or to continue the design of the second plane and alter that design and reform it to be able to accomplish what we need for the project. As well, we have to consider our budget and material selection for either our second design on the materials and what our budget is for the third plane. Thank you very much, and questions?
I'm a little bit confused because you said we chose the third design and you built the second design.
Well,
Why?
the thing that happened was last time when we presented our project, we were originally told just to buy the shell of the aircraft itself because our advisor told us it would have taken us way too long to design not only one, but we would have had to design two, as you've seen in the crash, to design two of these planes in the amount of time that we had to go to the competition. But when we came to the advisory board the last time, we were advised to try and build another plane on our own to be able to implement all of the mechanical design terms and things we've learned throughout the semesters. So we went ahead and we tried to do that. And unfortunately, we were, like as Richard said, we received our dimensions for the plane about 2 months into this semester, and the dimensions turned out being wrong because they budgeted themselves at a higher budget than they actually had. So they had to cut their funding, and they had to buy different components that were larger in size. So we went ahead and tried to gut the plane, which ended up not working so well because the foam itself, it's strong in certain degrees, but when you have really thin foam, like in this case with the expanded polystyrene, and you try to balance the wings on it, it causes a lot of bending. So we weren't able to try and fly it after that point, but that's pretty much the reason why we decided to build our own plane for this project.
Did you learn anything from the crash as to what the cause might have been? Was it?
Yes.
But
We
two
learned a
crashes,
lot.
by the way.
Yeah.
There's
Was-
two crashes, right?
Yeah.
We learned a lot.
What was it? A fatigue failure or what?
It was, it's funny. We were actually, in this crash that happened, we were actually kind of in a rush to try and get the plane ready to go to a showing in the Smithsonian. So it was on a day that was really windy, and we knew that it was probably a bad idea to try and fly it. But we had to try and do it anyways because we had to have a video of flying for the team to bring to the showing. So we put it together, we balanced it, we got it up a couple times, and the wind just blew it out of the air. So the third time, we decided to try and get it up, and we hit the throttle really fast, and it took off, and it went up about 100 feet, and it was in the air, it was fine. But then, like I said, those gusts of winds were coming, and it knocked the left stabilizer off. So the plane, we ended up losing control of the plane. We couldn't recover it, so it took a turn, and then we tried, because we had put reflective tape on it to see which side was like up and down. We tried to figure it out, but it was too far away, and it just came straight down.
One of the main
When
things.
you lose a stabilizer, it's over.
Yeah.
Yeah, and then we lost the second stabilizer, trying to regain control.
Yeah.
One of the main things we learned is that fluids don't scale well. So maybe 15 mile per hour winds wouldn't be a problem for a big airplane, but for a little model, it's a big
Yeah.
problem. So
Especially with this one, we didn't have landing gear, so it was all hit or miss. We had to throw it and be able to get it as soon as it went up, or that was it.
Any other questions? All right, hearing none, seeing none, thank you very much.